Hello, everyone. My name is Mansoor, and I'm here to introduce our conservation robot. As we all know, in California and the West Coast, we've seen a surge in wildfires, and these wildfires are due to climate change. We're seeing higher temperatures, and higher temperatures are contributing to longer and more intense fire seasons that are harder to deal with. The last 2 years alone in California, we've seen 3 million hectares burned down, and wildfires are classified as ecological disturbances. And sometimes these disturbances can be beneficial because when the ecosystems rehabilitate, you'll see an increase of species, more species will flourish, and it promotes biodiversity. However, they're also detrimental because they end up wiping populations of plants out and putting them on the endangered species list. And once we have plants that go extinct, we know that we'll never get to get them back. The California Department of Fish and Wildlife put a list out of a little less than 100 species of plants that are endangered, and the number one threat to these endangered plants are wildfires. So when these wildfires dwindle the population of these plants, they have to be reintroduced into their ecosystem. And we are hoping our robot helps to aid in this process. We're using an array of sensors and automated driving, and we're hoping to automate the reintroduction of these plants.
Hello, everyone. My name is Mario Martinez, and I will be talking about the sensors. Our group will be creating a robot that can effectively locate viable areas for reintroducing plant life. We have an atmospheric sensor which measures humidity, temperature, pressure, and CO2 levels. We also have a photoresistor which measures sunlight levels. Now, these are very important because if any of these factors is too high or too low, it is very difficult for any plant growth. In addition, we have a moisture sensor that goes directly into the ground and is able to tell us if an area is too wet or too dry, which is yet another very important factor for plant growth. Now, having these three sensors plus a driving sensor can be quite a big problem. It's a problem because the red board, it's about the size of my palm. Now the question is, are all these sensors with their own individual wires, will they all be able to fit in one red board?
Hello, my name is Patrick Lee, and I am the less handsome half of our coding team. So you might be wondering, how do we fit all those sensors and all those motors onto one board? The answer is, we didn't. We instead had two boards, which I nicknamed the Penelope and the Kishi, one for driving and one for sensing. The two boards will communicate with each other through a set of pins that are both set to input and output, meaning they can change each other's pins and the code will react accordingly.
Hi, I'm Eric, and I'm the leader of the group. I did all the design and fabrication of the 3D printed parts. This is the second major project I've done that utilizes my newly learned CAD and 3D printing skills, so it was a fun experience. My job was essentially to build up the skeleton of the robot. Let's go around the chassis and take a closer look at some parts. So the biggest system we have is the steering. There are round slots in the corner of the chassis for ball bearings to let the wheels turn smoothly. We decided to have the motors zip tied to these wheel blocks, so I left grooves for the zip ties. These parts are secured with some tightly fitting printed washers pressed on to the end of the shaft. So now we have wheels that can spin, but how do we make them steer? We're using a servo to control our steering. I hooked up the steering bar across the front wheels to turn them. If you ever played a game from the Halo series, you'd recognize this iconic vehicle called the Warthog. It steers with all four wheels, with the back wheels turning opposite from the front ones. I thought, that seems like a fun idea. So I added some more steering bars, as shown. Unfortunately, after all this design, our servo was simply too weak to actually use this system while it was on the ground. Moving on to this side of the board, here we have some modular mounting holes. Attached here is our probe arm mechanism. I printed a mounting bracket, a probe arm, and a mount for our moisture sensor. and assembled them like so. The moisture sensor did not come with mounting screws, and there were solder spikes on the back, so I printed pegs and just used hot glue to attach it. I designed the probe arm to fit over our servo horn and have zip tie slots for cable management. Here we have our seed dispenser. The servo turns and dispenses one seed at a time. For this demonstration, we are using steel balls as our seed analog. So we have all this hardware, how do we make use of it?
So for software, we have 2 files, one for each board. The Penelope board, which is responsible for driving, has a bunch of its code derived from Project 5C of SparkFun's Redboard kit, which covers autonomous driving. However, we did make a few modifications to the code, including a new timer variable, which we initially set to 0 and increment each loop. However, this incrementation does not happen when the robot is trying to turn, as we don't want it to try and stop and start sensing in the middle of obstacle avoidance. Once a certain value is reached, the timer will force the robot to stop, pause all the motors, and send a signal to the Kishi board, which is our sensing board. The motors and movement will not resume until the Penelope receives a message back from the sensing board.
I'm Richard Key, and I helped with some of the other code. So I created a flowchart to help explain the sensing code. In the setup, we have the variables I2C, the libraries, setting up the servo, and setting up OpenLog. First, we check to see if we receive a pulse from the driving board, and if we're not recording. If so, then we start recording data. If we're recording data, then we print data to the SD card after getting the readings using OpenLog. Then we drop the probe arm, which has the moisture sensor on it, and check to see if the conditions are suitable for farming. If so, then we drop the seed, and then we stop recording and send a pulse to the driver board to continue driving. After that, the loop continues again.